All right, this is Ryan Quinn from AIS, here to provide a real quick status update on our work towards adding Zen PVH support to the Bareflank hypervisor. Right now we're doing everything in our hyperkernel repo on a separate branch, but eventually we will actually be breaking up our work between the hyperkernel repo and our PV interface repo, which will actually have the Zen specific components in it. The research that we're doing is specifically geared towards adding Windows Dom0 support to the Zen PV interface. So we would like Windows to actually be Dom0, or frankly any other operating system. We really don't care what operating system it is. Right now our focus is Windows. And it is for Dom0. So Windows guest support, Zen already supports, but actually being able to run Windows as Dom0 itself is a new thing. We would also like our Windows Dom0 to be PVH and deprivileged. So what that means is that instead of Dom0 running in PV, which usually PV is the interface that Zen uses, PVH for Dom0 is a relatively new thing that's still being completed. We would like that to leverage that PVH interface for Windows, and we'd like it to be deprivileged. And what deprivileged means is that Dom0 itself doesn't actually have access to the guests. Now, I'll get into some of the details here on how we plan to do that. But specifically Dom0 itself, we would prefer it not be capable of actually accessing any of the resources that the individual guest virtual machines are running are capable of, which is very different than what you normally see in Zen. There are several other goals that we have. We would like to actually remove the scheduler from the hypervisor itself. So the hypervisor, our goal is really to just manage resources. To do scheduling of virtual machines, we're trying to transition that actually also to Dom0. One of the things that we found while working on the OpenXT project is that there are issues with having two schedulers running simultaneously. The Zen scheduler tends to conflict with the Dom0 scheduler. So if you happen to have resources that are running in Dom0 that need more real-time execution, that starts to become a problem because Zen itself is not aware of the various different processes that are running within Dom0 and what types of timing constraints those processes might need. So getting rid of the Zen scheduler and moving all scheduling to Dom0 allows Dom0 itself to manage those resources appropriately. Also, by doing that, it means that Zen itself, or the hypervisor itself, doesn't actually have to do any power management. So in this particular case, since we're leveraging a Windows-based Dom0, we're not only able to leverage the scheduler within Windows to schedule virtual machines, but then we're also able to leverage the power management features of Windows, which means that we can get very good battery support on more mobile devices like laptops and tablets, which is a big focus for our research. Another one of our goals is to remove the need for external interrupts within Dom0. External interrupts is what that basically means is that every single time an interrupt fires, the hypervisor itself has to trap. That is a source of a lot of performance degradation on the system. And Dom0 tends to be, since it usually has most of the devices, it tends to be the sort of virtual machine, if you will, that receives the most number of interrupts. And so if we can remove the need to have external interrupt support within Dom0, what that means is that interrupts can fire straight to Dom0 without the need for trapping to the hypervisor. Now, external interrupt support is still needed for guest virtual machines, and if you do VTD pass-through to a guest virtual machine, you're still going to end up having interrupts having to be trapped in those particular cases. But at least the vast majority of interrupts that are coming in through the system are going to Dom0, and they don't actually need to be trapped. So that's another one of the goals for our research. And then disaggregation would be the third major goal that we have. So disaggregation is actually kind of necessary to get Windows to work. A lot of the resources that Zen provides within Dom0 are Linux specific. So if we attempt to try and get those to work, we essentially have to port those tools to Windows. Some of them are very bash heavy, so that's not necessarily a great position for us. So just to be able to get Windows Dom0 support to work, we actually have to disaggregate Dom0 in the process. But there's actually another reason why we want to do that, and it's from a security point of view. Once again, we want to deprivilege Dom0, and there are certain resources that execute in Dom0 that sort of give information about what the guest is doing. And so we want to disaggregate that as much as possible. So really, Dom0 is managing whatever devices aren't being passed through to other guest virtual machines. It's scheduling virtual machines and managing the hardware platform itself. And that's really it. Doing things like starting and stopping virtual machines, or XenStore, and other resources like that, as well as devices that we can actually take from Dom0 and pass through to other guests, are all things that essentially we're trying to research on this project to keep Dom0 as deprivileged as possible, while still allowing us to leverage operating systems other than Linux. All right, so the first thing we need to do to demonstrate this is to provide rather to actually get the hypervisor started. Now, Bareflank is very different than other hypervisors. Bareflank itself is a self-contained ELF binary that we can load from any point. And so to do that, we've actually created our own sort of execution environment for Bareflank. And then we provide a very simple ELF loader that allows us to load it from essentially any point. So you could, for example, load Bareflank while you're firing up EFI, and then boot whatever Dom0 operating system you want from there. That's really kind of the use case that Zen currently has. But you can also start Bareflank actually after the operating system's been loaded and execute from there. Now that's kind of like what you would see in sort of type 2, like Windows or like a VMware Workstation or VirtualBox. The difference is that those types of hypervisors don't start VTX on the host OS. So they only leverage VTX for the guest virtual machines. In our particular case, when we start Bareflank after the operating system is booted, we are essentially rooting the operating system. So it's very much like a VMX rootkit, where we basically load the hypervisor and sort of take control of the OS from that point in time. Now, if we're being security conscious, we're going to want to start Bareflank from EFI and boot the operating system from there. But if from a development point of view or from a non-security point of view, it's much more convenient to start and stop the hypervisor from within the operating system, so you're not constantly having to reboot. So in this particular case, that's how we're going to get this started. So from here, we're going to go ahead and start the hypervisor. All right, that's it. So now, essentially, the operating system, Windows itself, is now running under a virtual machine. Now, there's really, as you can see, there really isn't any difference as far as you can tell. We've written Bareflank in a way where really the only traps that occur in for Dom0 when this is happening are CPU ID instructions, or if the operating system itself attempts to try and break out of its container. So the goal is to try and, from the Dom0 point of view, keep the number of VM exits to a minimum. As you can see, everything's kind of running normal. And I am doing the screencast live on this system while we have essentially rooted the box. So as you can see, audio and video is still working. Everything is working as it's supposed to. To prove that the hypervisor is actually running, we can go ahead and ACK on the hypervisor, and you can see the ACK was successful. If I stop the hypervisor, so now I've actually removed the VMX rootkit, if you will, and we try and ACK the hypervisor, you can see that now it's no longer there and no longer able to communicate. All right, so we're going to go ahead and get this going again. I can also dump its internal ring buffer, and so you can see the hypervisor is actually now running on all 12 cores on my box, and everything's up and running. So if you don't run any guest virtual machines, you can pretty much run this, and as far as the system's concerned, nothing's really changed other than the fact that CPU ID instructions are slower. That's about it. But so long as Windows itself stays within its container, there really is no performance impact for doing this. Maybe in another screencast, I'll provide some PC benchmarks We have done those in the past, and there is no noticeable difference between running Bareflank and not running Bareflank. And actually, in some cases, we've seen performance increases, which is probably due to some caching improvements with VTX turned on. All right, let's go ahead and get a guest virtual machine up and running. So to do that, we're going to have to, so we've got the hypervisor running. As you can see, once again, we've got it, we did a dump just to make sure that the host OS is now in a virtual machine. And so we technically have a Windows PVH Dom0 right now. Doesn't do a whole lot, but it's there. Now we want to fire up a virtual machine. And to do that, we're going to execute bfexec. Now, bfexec needs to be told what virtual machine to run. The virtual machine in this particular case is a custom-built Linux kernel that has a netramfs. The init process we replaced with a simple Hello World sort of application that really all it does is it tries to read a Bareflank specific CPU ID leaf, which is its ACK back to the hypervisor, and then sleeps for a second and then just continues doing that over and over and over again. Let's go ahead and fire this up. Now, unfortunately, normally you would actually see this thing booting live due to the fact that it has serial support and don't have like a further screencast ability to output the serial dump. So once the guest virtual machine is up and running, we can actually go ahead and do just a simple make dump, and you can see the output from the hypervisor. So same thing, hypervisor is running. This is the vCPU ID for the guest. This is just a bunch of garbage that we're doing for debugging. So the status update is very raw. But you can see here that the application has successfully executed with the Linux kernel, and it is now hacking to the hypervisor. And we can go ahead and keep doing this, and you'll see that it's just growing because it's essentially just executing and sleeping over time. So every single second, it then wakes up again and outputs to the screen. So that's basically a guest virtual machine running in the background, pretty much nonstop. Now, if we go and look at Task Manager, we can see here that we go and grab the actual name, bfexec. We can see that bfexec is actually executing, and it's taking up a very small percentage of our CPU usage. Once again, this is because Windows is actually scheduling the virtual machine for us. Bareflank isn't doing that. And since the application itself is sleeping for a second and then executing, it's really not doing all that much. This is kind of an important thing to notice, is that it is a full Linux guest virtual machine. So it is running Linux. It is having to schedule the process within Linux. So whatever overhead that Linux provides is relatively minimal in this particular case. And as you can see, we're really not consuming all that much for the guest virtual machine as it executes. Now, once again, it's still kind of doing its thing. Now, Windows itself, like I said before, is a PVH Dom0, which means that it itself is also in a virtual machine. But even though it's in a virtual machine, there are no external interrupts firing within the within Dom0 itself, so there's really no performance hit for Windows. The only thing that's really causes a VM exit within Windows now is, once again, the CPU ID instructions, but then also if when bfexec goes to execute, the exits that are occurring due to that are really the bfexec asking Bareflank to go and schedule a different vCPU, doing the VMCM swap, and then executing that guest. But because Windows itself is actually scheduling bfexec in this particular case, it is capable of ensuring that bfexec, rather that the other applications that are running within Windows get whatever time they need, even while bfexec is executing nonstop. So that allows us to do a whole bunch of fun kind of things. So, for example, right now I'm still doing the screencast with all of this running live within Windows, but I can even do some fun things like play a video game. Now, one of the cool things about this is that Windows itself has full access to all the hardware, so it is still running in a virtual machine, similar to PVH Dom0 for Linux, but we can actually take advantage of all of the features that Windows provides, including full 3D support, and audio, disk, everything. So all of this works pretty much flawlessly. Now, the machine I'm running on is a relatively decent computer. It's a Intel 8700K with a NVIDIA, what's the card in there? 1080 Ti. But I'm getting 160, 170 frames per second, as you can see. And game works without a problem. Although the screencast software probably makes the game look a little choppy. On my box, it's running nice and smooth and just like it normally would, regardless of whether or not the hypervisor was running. Alright. So, that's pretty much it for the status update. We have Linux guest support. We have support for Windows Dom0. And so what's left to do is really the big question. Well, to start, we need to really start deprivileging Dom0. So there's a lot of work that has to be done to get that complete. So the first one is that we have support for EFI, but we've got to actually launch these guest virtual machines from EFI. So that part is we still need to do. Once that's done, then we can actually remove whatever resources the guest virtual machines needs from Windows prior to Windows booting. So that Windows will still have to execute bfexec, but it won't actually be responsible for loading the guest virtual machine, which means it won't see the memory associated with that virtual machine, and we can properly set up VTD to prevent Windows from actually being able to modify via DMA anything within those guest virtual machines, as well as eventually down the road be able to start doing PCI pass-through. So we actually got VTD working. PCI pass-through is what we're completing right now. We hope to have that done very soon here. It's actually, once you kind of get it turned on, it's not that much harder to do the pass-through part of it once you already have VPT and interrupt routing working. The other thing is, on the deprivileged side, we need to also get XenStore up and running in its own guest virtual machine. XenStore itself, we don't want executing in Dom0, so we got to do that part. Getting multiple guests to work. Right now, we only support one guest executing, but eventually, very shortly here, we'll have more than one. There's a whole bunch of cleanup that has to get done. We've got some registers that are still being passed through to the guest, specifically serial for one of them. But then two, also, there's just some minor ports that we need to actually to emulate properly. Finishing up VTD, and then finally, really the big thing that needs to be finished is front and back drivers. So our goal is to try and get multiple virtual machines up and running that allow us to do Xen front, Xen back. To do that, to start, we're going to take the NICs and we're going to pass them to a guest virtual machine using VTD, and then we'll have another virtual machine that can that'll have the front drivers that can actually then connect to our sort of NDVM, as it were, that what we call like a network domain virtual machine, which has the NICs pass through to them, and that allow the other guest to basically get access to the NIC and download files and do that kind of thing. The other thing we want to do is fire up the Windows PV drivers in Dom0 so that we could kind of do like a reversal where you have a guest virtual machine that has control of the NIC. So Windows itself doesn't actually have any network devices, but instead it has the Xen front drivers and gets its network through the NDVM. So that's another test that we want to put together and demonstrate. So that's essentially the work that we still have to do for our research. And with that, I thank you for your time.